Dr. Chu Rui is a senior scientist at the Institute of High Performance Computing under A-Star Singapore. His research focuses on the study of solar energy and solar cities. His presentation is titled Significant Carbon Mitigation Potential from Installed Rooftop Photovoltaics in Singapore. Dr. Chu Rui, please.
Hi, good morning. So thank you very much for the introduction. Nowadays, cities take around 3% of land surface on Earth, but account for 17.5% of all energy consumption and 18% of all CO2 emission. So in this sense, actually, cities are the main battlefield for climate change mitigation. In this background, the Journal of Advances in Applied Energy actually has published an editorial arguing that time matters for smart balancing of variable renewable energy supplies, maximize the benefits of energy prosumers, and optimizing energy system integration. During the past few years, studies has already suggested that solar energy is effective for this integration or renewable energy transition. To facilitate this process, we've already developed the concept called a sustainable solar city, which is a sustainable power system to effectively connect and store solar energy and flexibly power a variety of urban sectors. So we developed this concept, including 6 modules. In the past study, I've already touched all these 6 modules, but today we want to focus on the last part to quantify the potential carbon emission from the solar photovoltaic electricity generation. To achieve that, we developed a research framework. It has 3 modules. First, we segment installed PV areas from satellite imageries, which has high spatial resolution. And we use this we achieve this by using advanced deep learning-based semantic segmentation network that we developed. Then, second, instead of just simply accumulating the total installed capacity, we estimate the annual electricity generation of the installed PVs. So in this case, the result is going to be more accurate. Lastly, we integrate life cycle assessment to quantify this carbon estimation, carbon reduction potential. As a case study in Singapore, we utilized around 85% of areas for training this deep learning network, 15% for validation, and 5% for testing. The plots of A, B, and C in figure 3 shows the rooftop areas containing the PVs. B, the segmented PV area in the raster data format. C, that is polygonized PV area to regularize the boundaries. So there we achieved a satisfactory and even improved result by using the model we developed called the Deep Solar PV Refiner. And the benchmark is the well-established Deep Lab V3+. I guess some of you may be quite familiar with this. So at this stage, we can visualize the spatial distribution of the installed PV areas in all districts in Singapore. So you're going to see that the Tuas Changi Airport, West Coast, including Jurong Island, has the largest PV installation. According to the statistics, which is categorized by land use types, we find that the industrial, port, and airport and residential area has the largest installation, taking around 14.5%, 14%, and 8% respectively. Further on, we estimate this annual solar PV potential on 3D urban surfaces on the left side. The model we developed, which considers the influence of cloud cover, shadow from surrounding buildings, PV conversion efficiency, PV installation layout, and performance ratio. So in this case, the spatial distribution pattern is a little bit different. You're going to see Tuas Changi Airport have a larger proportion, while West Coast has a smaller proportion regarding annual electricity generation. It is because of the shading effects from the surrounding buildings in urban areas. Okay? Further, we modeled the life cycle assessment to track the spatial associated footprints of PVs during the whole life cycle. It has 4 stages, including PV manufacturing and production, ocean and road transport, PV operation and maintenance, and finally, end-of-life processing consisting of recycling and waste disposal. Further, we can calculate or estimate the carbon emission difference over these PVs compared to the local carbon emission factor in Singapore regarding the electricity generation, the grid set. Okay. And specifically, we considered these footprints according to the PV market sharing dataset in Singapore, mainly taken by the 5 countries of China, Canada, Germany, Japan, the United States, and Singapore. You're going to see actually China and Singapore, the 2 countries, takes more than 18% of the PV market sharing. We also modeled the different electricity generation and the carbon emission from 2 major types of PVs, which takes around 14% for normal SI PV and 14% for multi-SI PV. Okay? Then, to be short, we finally get a result. It shows that in average, the installed rooftop PV can generate around 300 kilowatt-hour electricity per square meter in a year, which will require around 1,000 megajoule energy input, okay, for generating 1 kilowatt electricity. Regarding the carbon emission rate, the figure is quite small. It's around 13 diagram CO2 emission for generating 1 kilowatt electricity. This number is almost a 15% reduction compared to the previous study roughly 3 years ago. Regarding carbon payback time and energy payback time, it's getting shorter than 1 year. This is actually mainly because of the improvement of energy structure from over these 5 countries specifically, or a major contribution from China, I would say. So these 2 figures, previous study also did this investigation in Singapore, roughly conducted 5 years ago, and the figure was around 1 to 2 years. So we can observe the improved carbon mitigation potential, okay? So as a very short conclusion, I would suggest Singapore is one of the best cities to use solar energy. And there is significant carbon mitigation potential from installed rooftop PVs in Singapore, okay? We also have a poster in the poster station, and I'm very happy to discuss with you if you have any questions. Thank you. Thank you very much for your listening.
Thank you very much, Dr. Zhu Rui, for your presentation on rooftop photovoltaics.